Well, it gives me a great pleasure to participate in this conference arranged by Professor Manjunath Prasad to celebrate Professor Rao, C.R. Rao's birth centenary. And especially Professor Rao has contributed not just for statistics, but even for matrix theory. And I have done a bit of work. My special interest is in inference for stochastic processes, but however, I have done a bit of matrix theory connected with Professor Rao's results. So I thought I'll present them to you today. But since the time allotted to me is only about 25 minutes, it's not possible to go into the proofs of these results. So I will just highlight. So I'm going to talk about some matrix versions of covariance, harmonic mean, and other inequalities, which are connected with my work as well as Professor C.R. Rao's. So I would like to dedicate my talk to Professor Rao during his birth centenary year. And I'll take a little bit about a couple of minutes, maybe about his life story, a little bit. Professor C.R. Rao was born on September 10, 1920 in Hadagalli, in the current state of Karnataka, India. He grew up with 6 brothers and 4 sisters in a comfortable family environment created by his mother, A. Lakshmikantamma, and father, C.D. Naidu. Today, he is a living legend whose work has influenced not just statistics, but has had far-reaching implications for fields as varied as economics, genetics, anthropology, geology, national planning, demography, biometry, and medicine. We are celebrating Professor Rao's birth centenary, and I would like to present this lecture in appreciation and celebration of his great contributions to the subject of statistics and to science in general. I have written an article entitled C.R. Rao, A Life in Statistics for the series Living Legends in Indian Science in the journal Current Science in the year 2014, but I will not be presenting them here. I was a student of Professor C.R. Rao in my master's program at the Indian Statistical Institute, Calcutta, during the years 60 to 62, and later his colleague at the Indian Statistical Institute, New Delhi, during the years 1976 to 79, before he left for USA. It's a great pleasure for me to dedicate this work to my teacher, Professor C.R. Rao, during his birth centenary year. Our focus today is on some of his research works in matrix algebra and their applications to statistics. C.R. Rao has extensively used matrix algebra in his study of unified theory of linear models. He has shown that some of the important results in matrix algebra can be derived from statistical results. Rao derived seven inequalities in statistical estimation theory, one of which deals with the harmonic mean of positive random variables. I was able to generalize this result to matrix theories in the year 2000, and Rao gave also an alternate proof of this result using again ideas from statistics. And coming back to my own contributions, Kimmeldorf and Sampson published a paper in Journal of American Statistical Association. They derived a class of covariance inequalities. Now, I have been able to derive the matrix versions of these inequalities in the year 1990, and they were published in a volume which was released in honor of Professor C.G. Khatri, who was an expert himself in matrix algebra. We will now review some of these results dealing with the harmonic mean for positive random variables and some covariance inequalities. And it so happens that Professor Kubilisko and Hansen have derived recently, generalizing my results as well as Professor C.R. Rao's results in a very big fashion. I will just talk about a little bit about them. So the covariance inequalities, let's start with that. So suppose script A is an open convex subset of R2, and xy is a bivariate random vector with support A. So further, we'll assume hereafter they all have components x and y have second moments. And suppose you consider any function gxy for which second moment or variance exists. Let us take that. And suppose gxy satisfies this inequality which I have presented, x2 minus x1 times y2 minus y1 is less than or equal to gx2 y2 minus gx1 y1 square. Then Kimmeldorf Sampson proved that any function which satisfies any function g which satisfies those conditions will lead to the inequality covariance xy is less than or equal to variance of gxy. So this is what I mean by covariance inequality. So by choosing different functions g of this satisfying this condition, we can get a class of inequalities. A matrix version of this result was proved by me in 1990. So the result is the following. Suppose psi and a are two random matrices. Now here they are not random vectors or random variables, but random matrices. Suppose you have two random matrices of order R by S. And further, suppose that all the entries of these matrices have finite second moments. So let's say expectation by the matrix of expectations. So when you say expectation of a matrix, you mean matrix of the expectations of the entries. And let's say prime denotes the transpose of the matrix psi. So the result, so the covariance is done in natural way. Of course, matrices don't necessarily commute. So you cannot use the usual standard definition of covariance of random variables. So you use this, which I have denoted at the bottom. Covariance psi eta is by this. You have to make it symmetrized. So that's why you have to have psi minus expectation psi eta times expectation of eta transpose, and the next term take the average. And variance, of course, is the standard notation. So you can use these things and then develop matrix covariance of matrices, and then it turns out that if this so-called matrices commute, if the random matrices commute, then it reduces to the standard definition. That's what I have presented in this transparency here. So it reduces to the standard definition if they commute. If they don't commute, then you have to symmetrize, and that's why the earlier definition was there. So using this theorem, the theorem 1, which I have noted here, of course, the standard notation we write for a matrix is A less than or equal to B, of course, square matrices. If A is less than or equal to B, if B minus A is non-negative definite, and A is strictly less than B, if B minus A is positive definite. This is the standard notation for matrices. And the theorem 1, which I have stated, so if you have two random matrices for which the support is in a set A, and if you take any function G, which is defined on those space of matrices, products of matrices, then you can see that covariance psi eta is less than or equal to variance G psi eta, if and only if that condition on the matrices, which I have written at the bottom of the slide, if that holds. Of course, it looks very complicated, but for some special functions G, this condition can be verified, and then you get interesting results. Now let's look at some examples. Suppose I take the function g a b equal to a plus b by 2. So which is a very simple example, a function, and you can very easily check that a condition which I stated in theorem 1 holds, and that result to a very interesting inequality for matrices. Covariance psi eta is always less than or equal to variance of psi plus eta by 2. Notice that this inequality is in terms of, that means the variance minus covariance is non-negative definite. It's a inequality on matrices. So similarly, suppose I and eta are positive definite random matrices of order R by R. Then of course, and suppose you have A and B are symmetric matrices, and then you define GAB, and suppose they commute. Suppose A and B are matrices, if they commute, and GAB you define in the fashion A power half, B for half, then you get another application of this result. Then there is another inequality which comes up, which is a consequence of Cauchy-Schwarz inequality for matrices. Not many people know about Cauchy-Schwarz inequality for matrices, but for those who are interested, it is given in the book by Ibrahimov Kasiminski in 1981, and this is the result which is at the bottom of the page. Here you can see that expectation of psi and pros greater than or equal to psi eta transpose, expression of eta transpose inverse, expectation of eta psi transpose, of course assuming that mean is 0 and of eta and E, and then this is strictly positive definite. And a third example which comes up again for this, if you have any positive definite matrices, D plus D inverse is greater than or equal to 2i. This is easy to check for the matrices, and in fact it's a consequence of this elementary result. D half minus d to the power minus half square is non-negative. Non-negative means, as I said, non-negative definite. In particular, for negative positive definite matrices, using this result, you can show this condition, and as a consequence, you can derive following result. Suppose you choose the function g to be a times b, then you can show that applying the inequality, you can show that theorem 1 holds for this function. So in particular, if you take a equal to psi and b equal to psi inverse, you get covariance psi inverse is very less than or equal to variance of g of psi inverse. But psi inverse is identity matrix. So that's the psi inverse is psi times psi inverse, that is variance of identity matrix, which is 0. So because identity is a constant matrix, so variance is 0. This in turn implies expectation of psi times expectation of psi inverse is greater than or equal to I for any positive definite random matrix. So it's a very interesting result. So of course everybody knows psi inverse is the identity, but expectation of psi, remember psi is a random matrix, so expectation of psi and expectation of psi inverse is greater than or equal to I. So this was proved earlier by Browski and so on. And there are other results. Suppose we define a positive definite matrix A and B. This is a symmetric average. This is something analog of arithmetic mean. Then A hash B by this formula and A exclamation B by this formula. So then it's known. Ando is a specialist in matrix theory. He proved this inequality. A exclamation mark is less than or equal to A hash B, less than or equal to A triangle B. Generalizing this, generalize the arithmetic mean, geometric mean, and harmonic mean inequality for positive real numbers. This is corresponding inequality for matrices. So Ando proved from his matrix theory results a nice result like this: A triangle B is greater than or equal to half of A to the power Q plus B to the power Q to the power 1 by Q. And of course, he has ways of defining the Qth root and Qth power and all that. Under the commutative assumption, it can be checked, they're all equal. This A hash B is equal to AB to the power half, and it's equal to A to the power of B to the power half. So it was shown earlier by theorem 1 that it works for arithmetic mean and also for this function under the commutative condition. But it does not hold for A exclamation B. And this result is also known even for real valued random variables, it doesn't hold. And but the theorem holds for functions of this type, which I will not go into because lack of time now. So this is an open problem for all matrix theory specialists to find out whether the theorem 1 holds for functions of this type and also for the function A transpose B. So people, whether it holds or not. Now there is called harmonic mean inequalities. Rao 1996 proved the following result. If x and y are positive valued random variables with finite expectations, then expectation of 1 by, so this power minus 1 is here. So 1 by x plus 1 by y is less than or equal to 1 by expectation of x plus 1 by expectation of y. And this is a result for harmonic mean. So it's I know harmonic mean is familiar with those. So Rao's proof involves the use of Holder's inequality and the dominated convergence theorem. So he first discusses for a discrete case and extends the results to the dominated convergence theorem for the functions of random variables. Now this result was extended by me to matrices in 2000 in a journal called Students Magazine, which was published from Netherlands. And the result is following: if A and B are almost surely positive definite random matrices with these expectations finite, as I told you, expectation of a matrix means matrix of expectations. Expectation of inverse means you take the inverse first and take the expectation of those entries. That's what it means. And suppose that these matrices are there and this difference is non-singular, then expectation of 1 by A plus 1 by B is less than 1 by expectation of S plus 1 by expectation of B, and there is an inverse again. So this is a matrix for harmonic mean inequalities. And this result actually can be proved by 3 or 4 methods, and my paper contains the proofs of these results. So one method uses what's called Jensen's inequality for matrices. So all of us are familiar with Jensen's inequality for random variables, and here this is a Jensen's inequality for matrices. But for matrices, first of all, a notion of convexity for matrices has to be studied because people know about convexity for functions, and we also know about concavity and convexity for functions. But here is a convexity for functions defined on the space of matrices. And this convexity was defined by Davis in a paper in 1963. The references are all in my paper if somebody is interested. So for any fixed positive definite matrix M, the matrix valued function Gx is equal to 1 by M plus 1 by X. We can show that this function is concave in X or the class of positive definite matrices. So if you can define convexity, concavity is a consequence of a similar thing. People know about that. And hence you get this inequality. Expectation of 1 by M plus 1 by X is less than 1 by M plus 1 by X. And now you take expectations again, takes with respect to the probability measure of the random matrix M. On both sides, the result follows. Here, these are essentially something like conditional expectations given M, which I have not written here. So this is given M, you have this result, and then take overall expectation, then you get the result. And there are several other proofs which are I have listed in my paper also. So one is, for instance, interesting example is for any two positive definite matrices, G inverse minus H inverse is greater than or equal to H inverse times H minus G times H inverse. And this is a consequence of the fact this non-negativity holds. There is another result. If G is a positive definite matrix so that it is finite and non-singular, then you can get this interesting result. This I have already discussed a few minutes back. It's like expectation of psi inverse is greater than or equal to expectation of psi inverse. This follows as a consequence of theorem 1, which I have done that, and I have it displayed today. And the third inequality using this HND or positive definite random matrices, finite expectations, then you have this inequality. Again, this is a fact that's is a consequence of the fact that the function A, B inverse A is a convex function over the class of positive definite matrices. And the detailed proofs are given in my paper. As I said, my time is short. I cannot go into the details of these proofs. Now this is the recent contribution, that's 2017. These are called general mean inequalities. This is the work by Gibilisco and Hansen. And they refer to my paper as well as Professor C.R. Rao's paper. So I thought it's interesting to present their results in this conference along with our results. And that's what I plan to do. Now, this definition of general mean is very interesting. It subsumes all these other means which are in literature until now. So, for instance, suppose you take two positive real numbers. You have the arithmetic mean, which is x plus y by 2. The geometric mean, which is xy to the power 1/2. The harmonic mean is 2 by 1 by x plus 1 by y. And the logarithmic mean, which is x minus y by log x minus log y. So these are four types of means which we construct. And Gibilisco generalized all these, Gibilisco and Hansen, they have generalized all these results to what are called bivariate means, which I will explain in a minute. And all of these others have been special cases of that. And as I said, the results are known of arithmetic mean. We all know the inequalities of arithmetic mean, geometric mean, and harmonic mean. Now there is a course called logarithmic mean. So I have given the example here. Suppose if you have positive random variables. So linearity of expectation operator implies expectation of MAXY is MA of expectation of XY. Essentially what it means is expectation of x plus y by 2 is expectation of x plus expectation of y by 2. So the operator here is the average operator. Now there is a Cauchy-Schwarz inequality, gives you this so-called geometric mean. Expectation of MGXY is MG of expectation of x, expectation of y. Okay, so this is again a standard result. Cauchy-Schwarz inequality gives you this. Then Rao in 1996 with an additional proof in 2000, and myself in 2000, we proved that expectation of harmonic mean of x and y is harmonic mean of expectation of x, expectation of y, which I have discussed earlier. So Gibilisco and Hansen investigated the generality of this result, including the question whether such a result holds for logarithmic gain. Now I'll just give a brief information on that. So a bivariate mean, which generalizes all the others, are given by a function satisfying these various conditions. It's if you x and x, if you take x, the function is symmetric. And if you took x and y and take the mean, it lies between x and y. If x and y, x is less than x, y is less than y, then mean of xy is less than mean of x prime y, and the function is continuous and is positive and homogeneous. There is m of t x t y is t of mxy. And you can check that all these are hold for arithmetic mean, geometric mean, harmonic mean, and logarithmic mean. So this definition of bivariate mean is due to Petz and Temesi in 2005. And suppose you call this class of bivariate means as script m. So now you define a class of functions which satisfy the following conditions: is continuous function, monotone increasing, at 1 it is equal to 1, and t of ft inverse is ft for t positive. So let's consider the class of such functions. We will show you some examples later. And now introduce the mean. Mean of x and y is bivariate mean is called f of y times. So if you have x and y, it is y times f of y inverse x. And you introduce a function fmt is m of 1t for positive numbers x by t. Now there are examples. For instance, if you choose f function is 1 plus x by 2, you get the bivariate mean is arithmetic mean. If you take root x, it becomes geometric mean. If you take 2x by x plus 1, it becomes harmonic mean. If you take x minus 1 by log x, it becomes logarithmic mean. And there is one more which we can construct. All the functions described above given to the class f are their concave functions, and Gimelisko and Hansen proved the following result generalizing my work and Professor C.R. Rao's work. And that's this result. Suppose f is a function in the class f, the inequality expectation of mfxy holds mf of expectation of x, expectation of y for arbitrary positive random variables if and only if f is concave. And this generalizes our results. In particular, the result holds for logarithmic mean for positive random variables, and in fact, Gimelisko and Hansen extended this result for what are called operator means in the sense of Kubo and Ando. So these are Ando's paper has appeared in the linear algebra applications on concavity, and then of course you can see that the second paper, Ando's paper, 1983, and the arithmetic geometric mean, harmonic mean for positive definite matrices. So the result on arithmetic geometric harmonic mean is known for real numbers for the last 60, 70 years, but he has applied for positive definite matrices. Now, of course, Bobrovsky and Zakai, and they have done some results. Then this is the result paper I was telling, Davis paper, who extended the notion of generalizing the notion of convexity for functions of matrices. And this is the recent result of Gimelisko and Hansen, an inequality for expectations of means of positive random variables, which appeared in Annals of Functional Analysis in Italy. And then, of course, my paper, my result is generalized Kimmeldorf and Sampson. And then this is Kubo and Ando's result, which is I have explained. And this is the result which I have done on matrix version of covariance inequality. This is Gujarat Statistical Review, which is in honor of Professor Khatri, who has worked extensively with Professor Rao on linear models and matrix theory and all that. So they're both experts in their work. Khatri is an expert in matrix theory, and Professor Rao has done extensively in matrix theory, and his work in generalized inverses is very well known. And I have done this. I've contributed inequality for random matrices with application to statistical inference. It was published in a magazine called Student way back in 2000. And Professor Rao has written these 7 inequalities in statistical estimation theory. So these are all inequalities which are known, but his idea is to derive them through the concepts of statistics. And then, in fact, he's a more extensive paper and statistical proofs of some matrix inequalities. Well, thank you very much, and this concludes my lecture. Thank you.
Thanks for speaking.
Any questions? Yes. Is there any connection between your versions of matrix inequalities and many similar matrix inequalities proved by Rajendra Bhatia.
Well, the only thing I know is this paper by Jibelsko Hansen. They have unified all matrix, all sorts of means of inequalities. So that includes arithmetic mean, geometric mean, harmonic mean, and all that, including Ando's results. So whether it includes Bhatia's results or not, I have no idea.
They have matrix versions of mean value theorem, second mean value theorem, and Lagrange remainder, and so on. They are all functions of matrices, but scalar valued functions of matrices, and for them they are trying some kind of Taylor expansions, and in that context Bhatia has several interesting inequalities.
Probably it might be possible to extend those results to these ideas of Gibelsko and Hansen, generalizing all those inequalities to this. And then he has also inequalities and operator means and so on. So probably some of these might extend to that. So it's an open field now for general work based on their work.
Thank you. Thank you.
Thank you. Thank you.
Try to extend to n tuple. Then I think you get some of the difficult. I know that the geometric mean of tuple is a difficult problem. Arithmetic mean and harmonic mean. I don't know if you have tried some result for n tuple other than similar. I think you have to unmute.
I am not able to hear you.
Sorry.
I'm unmuted.
I'm sorry, I'm not able to hear you.
I have unmuted. Can you hear me now?
No, it's not able to hear.
Not very clear. Okay, I don't know what is the problem because
அவனுக்கு காது கேட்கல. பாப்பா சொல்றது அவனுக்கு கேட்கல, அவன் சொல்றது அவனுக்கு கேட்கல.
is it clear now?
Yeah. Yes.
Professor Prakasa Rao, you have to unmute.
Professor Prakasa Rao, you will have to unmute your system. Please unmute. It is muted.
Now?
Yes.
No, Professor. Now it is unmute.
Okay.
So I had just one remark that whatever you have presented, if you, I think for n tuples of matrices, if you try to extend, then there are many, but the geometric mean is a difficult problem. That, as far as I know, but I think some of the results will go over for n tuples. That's what I wanted to remark.
I would be interested in seeing that. Yes. Thank you.
Okay.